Okay, so far we looked at the three processes: stimulated absorption, stimulated emission, spontaneous emission, which happen when electrons are moving between multiple energy levels. We derived rate expressions for them. From that we got an expression for the energy density of the incident radiation. We calculated the ratio A to 1 by B and so on. So we were looking at all three processes as a whole, sort of a high level view. But while studying lasers, what we are particularly interested in is stimulated absorption, right? So we are now going to look at stimulated emission, right? So stimulated emission is what leads to a laser, light amplification by stimulated emission of radiation. So in this segment we are going to be looking at what conditions create stimulated emission and what conditions lead to a laser formation and so on. So when you have an atom, you have electrons at energy levels E1 and E2. Of course there are going to be multiple levels. For the sake of simplicity we just assume two levels, and when you're providing some sort of heat or light or some sort of energy, all these three processes will keep taking place simultaneously. There will be electrons moving from E1 to E2 because of stimulated absorption. At the same time there will be electrons coming down from E2 to E1 because of spontaneous emission as well as because of stimulated emission. Everything is going to keep happening concurrently, which is why the total absorption and total emission are going to remain equal to each other and the number of electrons is balanced. But that is the case in a normal atom, normal electron. But if I want to create a laser, I need stimulated emission. So stimulated emission should dominate over absorption and spontaneous emission. That is when I will get a laser. That is when particularly I will get an intense, coherent and directional beam. So coherent and directional are important points here. So we saw how repeated amplification is responsible for this property of lasers called intensity. Now there are two other properties, highly coherent and highly directional, and stimulated emission is responsible for these two properties. How? Let us quickly remind ourselves of what stimulated emission is. So you see that there is this incident quanta of energy which triggers all these electrons to give out their energy. And because this emission is triggered by this quantum, that is why all these released photons travel in the same frequency, same phase or constant phase difference, same direction. And in a previous segment, if you remember, we saw that these two things here, they are the condition for coherence. And same direction of propagation is what we call directionality. And these happen because of this triggering. So the point I am trying to make is that if you want coherent and directional light, you need stimulated emission. So if you want more light which is coherent and directional in nature, you need to make sure that stimulated emission dominates over stimulated absorption as well as spontaneous emission. That is when you will get coherent, large quantities of highly coherent and directional beams of light, and those are what you call lasers. So if we want a laser, we need to make sure stimulated emission dominates over the other two processes. So under what conditions will it dominate? Because generally we saw that absorption is equal to the sum of the two types of emissions. So now if I want one type of emission to become much higher than the other two processes, what are the kind of conditions I need to create? So we will see two subsets. First, stimulated emission has to dominate over spontaneous emission, and then it also has to dominate over absorption. We'll come to that. So rate of spontaneous emission should be much less than rate of stimulated emission, or RSP divided by rate of stimulated emission should be much less than 1. That is when you say this one is dominating, right? So these are again the rate expressions we derived, very simple ones. We are not bringing the n2 by n1, 8 pi h nu cubed, all that here, just the simple direct expressions we derived. A21 n2 upon B21 n2 rho nu d nu should be much less than 1. Of course the n2 and n2 get cancelled, and what you are left with is A21 upon B21 rho nu d nu. So A21 by and this thing should be much less than 1. That is when you say the numerator is very small and the denominator is very high. and that's when simulated emission is much greater than spontaneous emission. So A21 by B should be very small, and this is the expression we derived for A21 by B, 8 by h nu cubed upon c cubed, where you can see 8 by h c are all constants. So if you want this thing to be very small, the only thing which is in your control to do is the frequency. So you make sure that the light or the electrons you're dealing with are going to be at very low frequency, the atoms, in the sense that you choose a material such that it is going to emit light at very low frequencies. So you choose material whose electrons, depending upon your knowledge of the the energy gap between different energy levels in that atom and so on. These are intrinsic properties which have been studied and written down. So when you choose a material to make a laser, you choose such a material who emits light at low frequencies firstly. So again, same thing, if you take it this way also, A21 upon B rho nu d nu, this is the expression. Again, e power h nu by kt minus 1 should be much less than 1. So again, if this term has to be very small, then nu has to be very low. So what is the key takeaway from this point? If stimulated emission has to dominate over spontaneous emission, then we need to work at low frequencies. So choose a material whose frequency of light emission is low. That is the key takeaway from this first segment. Moving to the second part, simulated emission also has to dominate over absorption, right? So for that, rate of emission divided by rate of absorption should be much greater than 1. Note that this is the rate of simulated emission, this one is the rate of absorption, the denominator. So this again, you substitute the rate equations you found, most of the common terms get cancelled out. So N2 upon N1 is what you are left with. So here again, B21 and B12 are getting cancelled out. So I would like to make a small clarification about that over here. Here we assumed that B12 G1 by G2 is equal to B21. But G1 and G2 are generally, there is not too much of a difference between the degeneracy of two adjacent energy levels. So we can approximate G1 by G2 as equal to 1. So in that case, it becomes B12 equals B21, which is why here you cancel out both B12 and B21. Rho nu d nu, of course, it's the same term in the numerator and denominator, you cancel both. So N2 by N1 should be much greater than 1. What does this mean? The number of electrons in the higher energy level should be much greater than the number of electrons in the lower energy level. Now that technically should not make sense. That should sound like an incorrect statement, because these Pauli exclusion principle and all that stuff, which says, and even just intuitively, the lower energy levels are filled first and then only the higher energy levels start getting occupied. So even when electrons get excited from the lower level and go to the higher level, only a few electrons are going to be excited and going to be moving, and they are also coming back because of emission and all that. So ideally, it is not possible for the higher level to have a greater population than the lower level, but that is the necessary condition for a laser. So how do we achieve that condition? Using something called population inversion. Population inversion is the process in which you do something to ensure that the higher energy level has more electrons than the lower energy level. So how do we do this? We do something called pumping. So do we have a slide for that? No, okay, not in this PPT. We will be studying pumping mechanisms in detail in a subsequent lecture, but just to give you a quick idea of what happens, so you have some mechanism which takes electrons from the lower levels and keeps sending them to the higher level. This is not the usual absorption thing. Absorption happens when you just provide energy, the electrons take that energy and they get excited and they decide to jump to a higher level. That happens. But apart from that, you have a separate pumping mechanism which is going to keep taking electrons from all lower levels and throwing them to the higher levels. So these electrons, as they go to the higher levels, because they did not come there of their own free will, it wasn't a conscious decision by the electron to gain energy and jump up. It was forcefully put into a higher level. So this electron will immediately want to come down to its equilibrium state. and so if some such electron wants to come down to its equilibrium state, it will adopt this process of stimulated emission, and so the rate of stimulated emission increases. Also, because these extra electrons are going into the higher energy level, the population of the higher level increases, so N2 by N1 becomes much greater than 1. So that is inversion of population. So we will be studying inversion in a little more detail in a subsequent lecture. So if inversion doesn't make complete sense at this point, it is okay. What you need to remember are the conditions. So we need stimulated emission to dominate over the other two processes. So the conditions are: firstly, work with low frequencies; secondly, do something to make sure the higher energy levels contain more electrons than the lower energy levels. So yeah, so that is mostly about stimulated absorption. So you know how it works and under what conditions it can be used to produce a laser light. So to construct a laser, choose a material that will give fluorescence in the wavelength band of interest, meaning choose a material which will emit light corresponding to the frequency you require, because you need it to be in the visible spectrum, of course, if it is for a flashlight kind of laser. If it's for medical purposes, it might not necessarily have to be visible. So you have your requirements. Secondly, it is best to keep the frequencies low if you want laser, which we just studied. So yeah, choose a material according to the required frequency and wavelength. That's the first step. Choose the method of pumping to create and maintain inversion. So this we will be studying in detail, like I said, soon. There are different ways of creating that inversion, different mechanisms which can be used to take electrons from the lower level and put them in the higher level. So choose a suitable method which can not only create but maintain that inversion for long enough periods to generate laser light. Optimize the resonator for repeated amplification. So you set up that two mirror setup and you put your simulated emission mechanism in between in such a way that maximum light can be generated. So those are the steps, and again the components of a laser. Active medium is the material in which the laser action is achieved. So the material whose electrons are going to keep moving between E1 and E2. Pumping mechanism is the setup which is going to grab those electrons from lower levels and put them in the higher levels. Resonator is the setup containing two mirrors and the space in between, so that repeated amplification can take place. So yeah, that's segment 2. We will be looking at pumping mechanism in more detail and some types of lasers, some prominent types of lasers in the upcoming segment.